Hello, everyone. I'll introduce myself. For those of you who just walked in, I'm Michael Beyeler. I'm a postdoc at the University of Washington. And today I'd like to present a software package we've been developing that has to do with the research on blindness. And it's called pulse2percept, a Python-based simulation framework for bionic vision. As you may know, blindness is a real problem in the world, affecting up to 20 million people. And as the population ages, blindness gets worse because most causes are usually age-related and they're also disease-related. So two of the most common causes in the developed world of blindness are retinitis pigmentosa and macular degeneration. In both of these diseases, your light-sensitive cells in the retina, the photoreceptors, start to die, slowly turning you blind, either from the fovea outwards or from the periphery inwards. And although there's no cure for these diseases, researchers have been trying to come up with ways to restore sight in these individuals. One way would be to use gene therapy, to simply replace the faulty genes with the functioning ones. Another way would be to induce small optogenetic proteins that make the surviving cells sensitive to light again. And then third is the idea of an electrical prosthesis, kind of like a cochlear implant, where you have a microelectrode array sitting on the eye and sending electrical current to the surviving cells. And this is what I want to talk to you about today. So it is interesting to know that electrical prostheses are no longer just science fiction. They're out there. There are two devices already commercially available, developed by a company called Second Sight and another one called the Retinal Implant AG in Germany. One of these devices is shown at the bottom of the slide. It's the Argus 2 device developed by Second Sight. And the way it works is the patient is wearing a pair of glasses with a small camera embedded. And whatever visual imagery the camera records gets translated into a series of electrical pulses that are delivered to the array, the microelectrode array, sitting on the back of the eye of the patient. This device has 60 electrodes total. So if we think of an electrode in the array as a pixel in an image, we have roughly 60 pixels to play with. So we would expect that as we stimulate a grid of electrodes in the array, a patient would see a grid of luminous dots, right? And if you just had enough of these dots, eventually the patient could see again. However, from behavioral observations, we know that the story is not that simple. There seem to be spatial phenomena. For example, if we stimulate two electrodes and ask the patients what they see, like ask them to draw it out, that for some electrodes we would see luminous dots, but more often patients report to perceive these elongated and weird-looking shapes. Interestingly, these shapes are very consistent on a per-electrode basis and repeatable over different trials. And I'll come back to that later. There are also phenomena in the temporal space, such as twinkling or fading over time, and there are spatiotemporal interactions. So to understand where these distortions come from, I have to give you a quick crash course in neuroanatomy, or here the eye anatomy. So this is a schematic cross-section of the eye. We all know as light enters through the pupil, it gets projected onto the back of the eye, which is a thin nerve tissue called the retina. It's about the size of a postage stamp and as thin as the skin of an onion. And if we turn the eye on its head, so to speak, and zoom in on that retina in the back, we find a very densely packed layer, a neural network, where we have different nerve cells that take in light and transform it into electrical activity. The light-sensitive cells are the photoreceptors, probably all know that. So they are sort of the input layer. And the electrical signal of photoreceptors get sent to other layers of the retina, ultimately to the ganglion cells, which send an electrical signal through the optic disc via long wires or axons to the brain. Now, in disease, the photoreceptors, most of them are gone. So the idea of electrical prosthesis is to put a microelectrode array in these cavities. And there's different locations to put the devices. There's all sorts of devices out there that differ in their geometry, in their size, and location. And the idea is that if we stimulate these remaining cells, maybe we could fool the brain into thinking that we're still seeing. So 2 of the devices are highlighted at the bottom left, the Argus 1 and Argus 2 devices of second sight, Argus 2 being the current state of the art, if you so will. Because there's so many different ways to approach this problem, there is a whole amount of parties that are currently developing retinal implants. So we want to make 2 observations here in this world map. First of all, we're not on it. That's because we're not developing an implant. And the second observation we want to make is that the field is in the hands mostly of companies, of startups. So I've highlighted the 3 different companies who already have commercially available products. The third one soon to follow. And as a consequence of this, you kind of have to understand what it's like in the field and how we fit in. So there are all these companies who have their way of doing things protected by patent, closed source, proprietary software and data. And that's all fine because as corporations, they would like to protect their ideas and maybe also profit a bit off it. But it really hinders research if you want, because if we want to understand what patients see or how good these devices work, what we have to rely on is simulations that are provided by the very people who manufacture the devices. And sometimes the claims they make might be a little exaggerated, leading to unrealistic expectations. So yeah, essentially, it's really hard to know how the current devices work and what patients actually see when they use them. And this is really important, not just for researchers trying to study prosthetic vision. It's also important for patients and families to understand what they're getting themselves into, or for medical professionals who are trying to make a decision whether to implant or not. And certainly also for engineers who are trying to develop future and better technology. So what we want to do is 2 things. First of all, we want to play sort of the independent role and provide a fair assessment of the current state of the art in prosthetic vision. And we want to provide the means to improve the state of the art and help guide development of future technology. And we do this in 2 steps. First of all, we have developed what we refer to as a virtual patient, which is basically a computational model, neurobiologically inspired, and it can predict what the patients will see based on any given stimulation pattern. I told you before about these distortions, right? So here we're looking at an image of the back of the eye. You can see the optic disc on the right, where all the neurons send their axons to the brain. And on the left is an implant, the Argus 2, sitting on top of this neural tissue. And as I mentioned before, if you place an array on the ganglion cell layer, you are not just stimulating the ganglion cell bodies, but also their axons, just due to their location. And if you look at how neurons send their axons to the optic disc, it's in this very intricate pattern highlighted in green. Which means, if we place an electrode right there on this tissue, we're not just stimulating the neurons that sit directly below the electrode, we're also stimulating the neurons that send their axons through this point in space to the optic disc. And we believe that is what is causing these streaks that patients report. So I won't have time to go into the details of this model. You're welcome to look it up. It's in the proceedings paper. To give you an idea, we have developed a model that consists of a whole cascade of stages of linear and nonlinear processing steps that takes into account where the array sits on the retina, what input it gets, and then produces a predicted percept that we can validate, that we can compare to what patients are drawing and reporting. So in short, we have made sure that this model works across electrodes and patients and devices. We've developed it in close collaboration with Second Sight, and there are already companies out there who are currently testing it. And the second step is to make this model available as an open source Python package. You can think of it as a black box that abstracts away the intricacies of the computational model. So as a user, you specify what implant you want to use, where you're going to put it on the retina, what stimulus to put in, and the package spits out a predicted percept over time, so a movie over time if you want. The code is available on GitHub, so is the documentation, and you can pip install it today and try it for yourself. When we designed the software, we had 4 different design principles in mind. One is ease of use. We can do this by providing a hopefully intuitive API, provide help and documentation, and help users when errors happen to diagnose them and recover from them. We want to have a modular design because as the computational model keeps improving, we want to swap in and out certain parts of the model. This goes hand in hand with flexibility. We want to make users able to rapidly prototype and also integrate our tool with other libraries from the Python community. And for this, we also need to provide extensibility, a means to customize the model to your specific needs, to write your own implants, design your own stimulation protocols. So we came up with 5 or 6 SOP modules that logically group these different functionalities. One is the API, which is hidden to the user because it's imported into the namespace of pulse2percept. There's one that is concerned with everything implants, where you can design your own or choose from common ones. There's another one that contains all the intricacies of the computational model of the retina, one for the stimuli, and a bunch of utility functions. So next I want to run you through a basic usage example. And for reasons that will become clear in a minute, I'm not doing this in a live Jupyter notebook, but you're free to try it. Yes, there are 3 different steps to running a simulation. You set it up, you run it, and then you analyze the output. So to set it up, first of all, you import the package. We do this by convention as P2P, just to make things simple. And then you want to set up the implant. Here you can choose from common ones, as the ones I've shown you before. On the right is an Argus1 array. You can say where to place it on the retina and how to rotate it. And then you can start the simulation framework. This is where you choose the parallelization backend. Currently, we support Joblib and Dask. You can choose the number of workers. And from then on, the simulation is set for that particular device in a particular location. There's 2 more steps. You want to specify the retinal model. And here what we try to do is hide all the intricacies of the computational model to the user. We provide a number of setter functions that allow you to customize certain model parameters. For example, there's one that sets the ganglion cell layer parameters, and you can choose from published models, for example, or build your own. And then finally, you want to specify the input stimulus. There you want to tell the software, I want to send this electrical pulse to that electrode. So we do this most easily with a dictionary. And a low pulse train is shown at the bottom right. You will notice that usually people use square pulses. And for safety reason, every positive phase of the square pulse has to be followed with a negative phase of equal current, so the total current is 0. Otherwise, over time, current charge will accumulate and the tissue might damage it. So there are certain engineering constraints and safety concerns that we put in here build into the software. And then when you've done all this, you run the simulation by calling the method pulse2percept. And this does exactly what the name suggests. It takes in a pulse, a stimulus, and produces a predicted percept. And here's also the reason why I'm not doing this in a live demo, because this might take a while. So you're free to try, but you will need a couple of cores and some memory. After that, we provide a number of means to analyze and visualize the output. You can save the percept to a movie file with the help of scikit video, or grab individual frames via scikit image. You can visualize it using matplotlib, and that gives us, again, the image at the bottom right that you've seen before of the 2 percepts, one a focal point and the other a distorted shape. Of course, we want to make sure that users can customize, fit the model to their own purposes, and we do this via class inheritance. So you can write your own retinal implant or ganglion cell model or stimulation protocol by inheriting from the appropriate base classes. A word about computational performance. So the computational cost was really the main bottleneck when developing this software. And you have to think that the retina is typically modeled at 25 microns. So a rule of thumb, no pun intended, is to hold out your thumb at arm's length, and that is about a degree of visual angle. So we're sampling at 10% of that in space. And usually pulse trains modulate over a couple of microseconds. So to predict the percept over many seconds, we get usually trillions of elements in our NumPy arrays. And if you want to do element-wise operations on that or convolutions, that may take a while. So our approach here is to parallelize via joblib and task as much as we can. We found that we can treat spatial and temporal computations more or less separately. So in the first stage, we compute all the spatial interactions, so that in the second stage, we can parallelize over space and just compute the temporal response. Here I'm showing the execution time as a function of the number of spatial sampling points, and that increases roughly linearly as we would expect. I should mention that you have to do these computations only once per array and location on the retina. After that, everything is fixed, and we only have to worry about the temporal response. So for stage 2, we're plotting the speedup factor as a function of the number of CPU cores, and this is running on my particular desktop machine. We find with a low number of cores, speedup factor increases roughly linearly. I should say speedup factor here is calculated as the ratio of parallel to serial execution time. But then at some number of cores, maybe it plateaus, and the speedup factor decreases further on. Reason being that at this point, the simulation gets memory bound, so the overall speedup factor decreases again. You can see in the present stage, this is not really fit for real-time computation, but that wasn't its purpose. So it's better suited for rapid prototyping and trying out your ideas. In the future, we would like to make use of GPUs and cluster computing to speed up the computation. All right, so 2 things we wanted to do with this software was, first of all, we wanted to provide a realistic estimate of current prosthetic performance, right? And although there's no real way to know for sure, this is currently our best guess as to what patients see with the Argus 2 retinal implant in response to a natural movie. So on the left, you'll see some subway scene, and on the right will be our predicted percept over time. And this might not look like anything you expected, but this is what you can get with 60 electrodes. It's important to communicate that to patients, right? That they don't have some unrealistic expectation of an HD movie or something going on. And although you cannot make out details here in the distance, it is clear when a close-up person moves by that you can detect this motion. So even though the current state of the art might not allow for object recognition, it could still allow for spatial navigation. And after all, seeing this is better than seeing nothing. And furthermore, we want to use our software to improve the current state of the art, right? We think we can do better. So imagine we want to produce the percept of the letter E in the mind of the patient. If we just go forward and imprint the shape of E onto the retinal surface, as is usually done, then the outcoming percept might not look anything like an E. But with our software, we can solve the inverse problem, right? We can ask, what is the stimulation protocol I need to apply in order to produce the letter E? And with this, we can find what we find is a sparser activation of electrodes that produces something that more closely resembles the letter E. And the next step is actually to try this in real patients and see if it makes a difference. So in conclusion, I've introduced you to the concept of a virtual patient, which is this computational model that can predict what patients implanted with a retinal prosthesis see. And we can use this to provide a realistic estimate of current prosthetics and also to help guide development of future technology. And the open source implementation of this framework is called pulse2percept. It's available on GitHub and for you to install via pip. Thank you.
Questions?
Mm-hmm.
So I'm wondering, like, this last thing that you showed where you like figure out the stimulation to produce the E, but I'm wondering,
Yep.
If patients use this for a long time, will they like work with their own interpretation of, so like the natural phenomenon in the world is stimulating the retina in a particular pattern, and they might come to see like a naturally occurring E as something no longer looks like an E to them.
Hmm.
Do you know if that like might be an issue, or I'm just curious if that is.
Yeah, it's a very interesting problem. People have thought that because cochlear implants work so well, and the brain is able to adapt to this new distorted input, it might be the same might be the case for retinal implants. But here we're dealing with patients in their 40s, 50s, and so on, so their brain is not that plastic anymore, and it turns out that in the early layers of the visual system, there might not be enough plasticity for patients to come up with a new way of seeing the world. So another complication is that their retinas are degenerate. We're not really sure what the neural network looks like, and so we're trying to abstract away all that and just fit the input-output. And because it's validated across patients on their drawings, we know that this is what they see when we put this in, right? So this is a way to verify that what we put in is actually being perceived as what we think. Mm-hmm.
So in the real world, do your implants inadvertently activate any bipolar cells associated with cones, or is the perception totally black and white?
So epiretinal implants have been shown to directly activate bipolars, yes, and that activity will then sort of go on and activate other cells. As far as patients report, most of what patients see is whitish, yellowish, and that's as good as it gets today, because if you look at the size of the electrodes, they stimulate probably hundreds or thousands of cells, and it stimulates them unselectively. So we don't know what we're actually hitting. Are we hitting cones, rods, ganglion cells, whatever, but just kind of blasting this tissue, right? And trying to figure out what's coming out at the other end.
But you're getting less of it.
Possibly, yes. Yeah. Yes, it's really hard. Also because the patients are blind, right? How are you going to figure out like what they're actually seeing? It's, yeah.
I have a good question.
Uh-huh.
So you showed this image of what it would look like to the patient as someone walking past, you imagine what they would see. And then you said a statement that I was a little but to give them an idea of what, to give them a realistic perception of what you're capable of doing.
Yeah.
They can't see that either.
Oh, the patients, yeah, that's right. No, good point. No, the patients can see it, but usually they're accompanied by close family members, right, who then make the decision, or, you know, that information will be helpful, yeah, to the families, yeah. Yeah.
In simulations, are you limiting to 64 electrodes?
So we can do anything pretty much at this point. I've tried to show you simulations of real implants to get an idea of how good we are today. One thing people say is we just need more electrodes, right? We just need more pixels. But preliminary results from our lab show that might not be the case because of these streaks that are produced by these axon trails, right? If you put more electrodes on that trail, you're still going to stimulate the whole thing. So what we did is actually apply PCA to the output of all possible images to find the number of principal components, right? Then it can explain most of the variance. And we find the number of components being like an order of magnitude lower than the number of electrodes, meaning that there's a lot of distortions and a lot of information is lost. Are there more questions? Mm-hmm.
Yeah, this doesn't have a lot to do with what you showed, like maybe with the first slide. I'm really curious, what are the advantages of using such an electrode array in the first place over molecular biological methods? Simply because it sounds like your specificity issues are really higher than any improvement in the technology would actually let the solution become any better. Like the bottleneck is no longer the technology, but the intrinsic distortions in the tissue.
Yeah, so every technology has their advantages and disadvantages. The good thing about these arrays is that surgically they're relatively easy to implant. There are other technologies that rely on more smaller scale and more specific surgery, if you want. So that's a risk there. I should mention, though, that this is early days for the field. You know, the field has been around for, I mean, in this stage for 10 or 20 years. And this is the first software package made available to the community. So we are still learning a lot. And the next step will be to use smaller electrodes and larger sizes. But if you want to hear a specific disadvantage, for example, with the small photo switches, the optogenetics, is the temporal dynamics. So these proteins tend to be slower in their temporal response. So what will happen is that if you're out in the streets and a car rushes by, you won't be able to see it, which could be a big safety concern.
Okay, so
Okay.
I think we have to
Wrap up.
move on. Thank you very much.
All right.